stereogenic carbon, priority number 1 is, of course, chlorine. Priority number last, in this case, is definitely the methyl group. A little bit of confusion on the other two. Well, we go here, there's a carbon. We go here, there's a carbon. That's a tie. So we have to keep going to break that tie. This carbon is bonded to 2 hydrogens and a carbon. This carbon is doubly bonded to a carbon. That's effectively being bonded to 2 carbons according to the Coningo-Prelog rules. So he's bonded to 2 carbons and a hydrogen, so he wins. So this is therefore priority number 2. This is priority number 3. So we've got it set up for us to do it. The way it's set up, priority number last is already going back behind, so we're looking at it correctly. Going from 1 to 2 to 3 is counterclockwise. That makes this sucker in the S configuration. Rock and roll? On question 2, that first one, a couple of ways in which you could go about that. First thing you would do is note that, yes, we do have a stereogenic carbon. You would note that the 4 things bonded to the stereogenic carbon was the same in both cases. So that leaves only 2 possibilities. Either they're the same thing or they're a pair of enantiomers. My personal go-to is I sign R and S. I'm the one on the left. R or S?
R.
It's S. The hydrogen is coming out at us, which is a group of lowest priority. So our mind's eye is on the other side of the paper looking up. And going from bromine to hydroxyl group to methyl. That's a counterclockwise circle from that perspective. That makes it S. And the one on the right is also S. The hydrogen is pointing to the right, so our perspective there is being like on the left of the paper looking in. Going from bromine behind the paper to hydroxyl group in the paper to methyl group in front of the paper, counterclockwise, so that's S. Both S, they got to be the same guy. The other thing you could have done is they were written in the exact same format. That is, solid lines in the same places, wedges in the same places, dashes in the same places. If they're written, 2 years of speech therapy, so I can say words like written. I was one of these kids that couldn't pronounce R's. And I still, every once in a while, they weren't written, they were written. Where was I? Oh yeah, because they were written in the exact same format, you can play the switch game. We look at the 2, the hydroxyl group is in the same place, nobody else is in the same place. So you can get from the one on the left to the one on the right. If we say switch, the hydrogen with the methyl group, that would put the methyl in the right place. But then we'd have to make a second switch with the hydrogen and the bromine, put everything in the right places. 2 switches brings us back to the original compound, so they're the same thing. As we look at number 2, again, make sure that that central carbon is stereogenic. In this case it is. Make sure that it's the same 4 things around that guy. It is. So again, that leaves us with only 2 possibilities. A pair of enantiomers, or they're the same guy. They are not written in the same way. That is, now look at the wedges, and the one on the left, it's going to the left, the one on the right, the wedge is going to the right, so you really can't play the switch game here. You can always do the R&S gig. And also, in this one, I drew them in such a way that if you pretend there's a mirror between them, you can see that they're mirror images of each other. So given that the stereogenic carbon, mirror images of each other, they got to be a pair of enantiomers. Assigning R or S, the one on the left is S. The one on the right is R. So you can also do R and S to see that they're a pair of enantiomers. Looking at the third one, again, make sure you have the stereogenic carbon with 4 different things bonded to it, which you do. These are drawn as Fisher projections. They're not drawn as mirror images. I mean, if you pretend that there's a mirror between them, I didn't draw them to make that easy on you. So that's going to be a toughie to do it that way. So kind of the best way to do this one probably be the RNS game. Oh, well, I take that back. We can always do the switch game. You can always do the switch game with Fisher projections because there's no way to draw them differently. But doing RNS, the one on the left, what do you got? R. The one on the right? Also R, that makes them the same. Playing the switch game, we see that the CH2OH is in the same place, so we leave that alone. But everything else is not good. To get the methyl on the right, we could switch the methyl with the hydroxyl group, then we would have to switch the hydroxyl group with the hydrogen. That would convert the guy on the left to the guy on the right. 2 switches gives us the same guy. And then the last one, kind of a quick glance at this should show you that it's a pair of diastereomers. We have 2 stereogenic carbons. The uppermost of the 2 are mirror images of each other. The lowermost of the 2 are identical. That kind of by definition is stereoisomerism. We indicated 2 types of diastereomers that we would deal with, this and cis trains. Hypoguntas? Okay, number 3, 2-bromopropane has no stereogenic carbon, but 2-bromobutane does. Draw the R and the S. Some of you kind of drew structures that I couldn't make sense out of. I wrote you a little note if I couldn't, or I did something, put a question mark or something if I didn't understand what you were drawing. But basically it's just a case of the stereogenic carbon. I didn't specify how to draw it. You could have given me Fisher projection, some of you did. You could have wedged and dashed it, some of you did. Wedging and dashing it. And that's kind of like the classic wedge and dash structure. 2-bromobutane. This is carbon 1, 2, 3, 4. There's your butane. Here's carbon 2. There's going to be a bromine on it. That would have to be a hydrogen. So there's 1. There's the S isomer. Then just draw the R isomer. Again, multiple numbers of ways. And there's probably the most straightforward. Just switch a couple of guys. Okay, then there's number 4. Number 4 didn't go all that well. Write 3-dimensional formulas for all the stereoisomers of the following compound. Again, as far as writing 3-dimensional formulas, as far as I was concerned, you could do it however you wanted. When dealing with multiple stereogenic carbons in a compound, Fisher projections is usually the way to go. In fact, that's kind of 100% of the reason why Emil Fischer developed Fisher projections, because he was dealing with compounds that have multiple stereogenic carbons, the sugars. And he just didn't want to wedge and dash everything. So he said, heck with wedging and dashing. I'm going to invent a cleaner way. You certainly could have wedged and dashed it. Some of you wedged and dashed it beautifully. But the easiest way would be Fisher projections. Several of you had quite a number of structures down. Well, there are 2 stereogenic carbons in this guy. 2 to the end, there's only 4 possible structures. Only 3 possible structures if we have a meso compound. Is there a possible meso compound here? No, there isn't even a possible meso compound. A meso compound is when you have 2 stereogenic carbons that have the same things bonded to them. Well, here we have 2 stereogenic carbons, but the one on the left has a hydrogen, a chlorine, and the rest of it. The one on the right has a hydrogen, a bromine, and the rest of it. So there's no way there's going to be any sort of internal plane of symmetry in this guy. It just can't be. So no meso compound. You know, the cleanest way to draw the 4 would be as Fisher projections. The 1 carbon, you know, has a methyl group, a hydrogen, a chlorine. The other has a methyl group, a hydrogen, and a bromine. I mean, it wouldn't matter where you put these 3 things or where you put these 3 things. There's 1. Keeping the Fisher projection format, instead of the chlorine on the right, I can move it to the left. Keep everything else the same. That would be different. I could move not only the chlorine to the left, but the bromine to the left. That would be different. Keep everything else the same. And I could have the chlorine on the right here and the bromine on the left. Keep everything else the same. That would be the 4th possibility. And again, they didn't have to be drawn as Fisher projections. You know, I had the methyl groups, you know, up. However you wanted to do it, it doesn't matter. So then the question said, show pairs of enantiomers and show meso compounds. Well, there's no meso compound, so nothing to show there. As far as pairs of enantiomers, this is a mirror image of this. So these 2 guys represent a pair of enantiomers. And this is a mirror image of this. So these 2 guys represent a pair of enantiomers. And of course, you can assign RNS throughout, and that might help you determine who's enantiomeric and who's not. A couple of things that came up with some frequency. Some of you drew 3-dimensional structures showing just 1 of the stereogenic carbons. And then sort of claiming that 2 structures were a pair of enantiomers. Well, absolutely impossible to determine that if you don't know the geometry around the other stereogenic carbon. And some of you labeled a compound as, and you wrote enantiomer by it, or a compound and you wrote diastereomer by it. Well, enantiomerism and diastereoisomerism imply a relationship. It's kind of meaningless to point to a compound and say that's an enantiomer. What is meaningful is to point to 2 compounds and say these are enantiomers of each other. You can think of enantiomers, diastereomers as like brothers. You know, other than street slang, you don't call somebody a brother without implicitly, at least, acknowledging a brother to somebody else. I don't know if that makes sense or not. It does in my little Ted head. This is my favorite head. Coolio? Can the Nationals still pull it out? I got a couple of brothers like me born in D.C. One of them still lives back there. So we've been texting each other back and forth every other inning during the World Series. So that's been fun. Okay. were we talking about last time before the crucible?
Oh, stability.
We were talking about factors affecting SN1 versus SN2. We know all about nucleophilic substitution, first order and second order. We know that second order is a biomolecular one-step process that results in inversion of configuration. We know that SN1 is a two-step process, the rate determining step being leaving group leaves, forming a carbocation. And then the second step, the nucleophile attacks that carbocation. The question we ask is, how can we determine a given reaction whether it is going to go SN1 or whether it is going to go SN2? And we said that one factor is the nature of the substrate, or to be more specific in our case, as we're talking about alkyl halides, is the nature of the alkyl halide. Certain alkyl halides tend to go SN1, certain alkyl halides tend to go SN2. Some alkyl halides have no major tendency. As we'll see, they do have a bit of a tendency. And we had indicated that tertiary alkyl halides prefer SN1, primary alkyl halides prefer SN2, and the secondary alkyl halides can do both. Okay, why do tertiary alkyl halides prefer SN1?
Not as much of the localized charge
Okay, on what?
on the carbon.
Set of carbon of what? There you go. Exactly. Everything you said was correct. The tertiary guys tend to undergo SN1. The mere fact, when I ask a question like that, why do they undergo SN1? The focus needs to be on the rate determining step of SN1. Any step other than the rate determining step is irrelevant. Might be a bit too strong a statement. You gotta have nucleophile around or you're not gonna have nucleophilic substitution. But it doesn't matter how much nucleophile, what the nucleophile is, the nature of the nucleophile, anything like that. So you have to focus on the rate determining step. The rate determining step in SN1 is producing the carbocation. So that's what it's all about. Whoever produces a carbocation well will undergo SN1 well. Whoever produces a carbocation poorly will undergo SN1 poorly. So a tertiary alkyl halide is going to produce a tertiary carbocation. And as we indicated last time, relative to hydrogens, alkyl groups are electron releasing. So having electron releasing groups, we have a positively charged carbon, which is what you're going to have. The sp2 hybridized trigonal planar carbocation. Having alkyl groups here, rather than hydrogens, these guys are relatively electron releasing, which is, I mean, that's the way organic chemists usually phrase it. Alkyl groups are electron releasing. But what is to say the exact same thing is to say that hydrogen is more electronegative. They're less electronegative than hydrogen. Just flipping that around, they're more electron releasing than hydrogen. So electron releasing tends to minimize the size of this positive charge. They share in a little bit. Little tiny partial positive charge, little tiny partial positive charge, little tiny partial positive charge. Still bears the bulk of the positive charge for sure, but a little less than a full positive charge because of the electron releasing effect. Compared to if these guys were hydrogens, where there is no electron releasing effect, minimizing this positive charge. Okay, so this is true because tertiary carbocations are relatively stable. It's important to appreciate we're still talking about an ion. Organic chemists say all the time tertiary carbocations are stable. When we say something like that, we mean compared to other carbocations. Certainly not compared to, say, neutral molecules. They're still an ion. Still want to hook up with something that has negative charge. Okay. The trigonal planarity of this decreases the steric hindrance. So the nucleophile can get in here easily. Does that help? No, that doesn't help. That is completely irrelevant because
It happens outside the rate determinant.
it happens outside the rate determining step. That's not the rate determining step. The rate determining step is forming the carbocation. Subsequent to that, nucleophile attacks the carbocation. It doesn't matter how easy it is for the nucleophile to attack this carbocation. That is not going to speed up this process at all because forming the carbocation is a much slower thing. That is the rate determining step. The only way to get SN1 to go faster is to somehow speed up the carbocation forming step. The only way to get SN1 to go slower is to somehow slow down the carbocation forming step. The other step simply doesn't matter in terms of how rapidly this thing can happen. Okay, primary alkyl halides tend to go SN2 because well, if we have a couple of hydrogens here, they don't form carbocations very readily. Does that matter?
It goes SN2 because less steric hindrance.
Okay, that's the dominant factor. It can go SN2 because minimal steric hindrance. Having a couple of hydrogens here, rather than alkyl groups, less, well not here because this is a carbocation, but having a couple of hydrogens on the alkyl halide, less steric hindrance for the nucleophile to get in there. But how about the notion of the fact that primary guys don't form carbocations well? Is that a factor in their preference for SN2? Most of you have an idea, but you're afraid. I know, I see fear. Oh, I don't bite, I snicker, but I don't bite. Yeah, it's a factor. Sure, it's a factor. There are basically two ways you can win a race. You think about it, you know, SN1 versus SN2. Either you go faster or make the competition go slower. The lack of steric hindrance makes these guys do this faster. The relative inability of these guys to form a carbocation makes SN1 for these guys go slower. So their inability to form a carbocation hinders their ability to do SN1. Their lack of steric hindrance enhances their ability to do SN2. SN2 is the winner. That's all I gotta say. Is that cool? Of course it is. Okay, a second factor affecting whether something goes SN1 or SN2. take a look at the nucleophile. We can talk in terms of concentration of the nucleophile. You know, and we could talk in terms of the strength of the nucleophile. In other words, using a good nucleophile versus a less good nucleophile. How about concentration of the nucleophile? If we increase the concentration of the nucleophile, in what direction, towards SN1 or towards SN2, will we be pushing this reaction? We got a 50-50 shot there. How come?
Because the nucleophile is part of the rate determining.
Bingo. If we increase the concentration of the nucleophile, it's going to speed up SN2. Precisely for what Jagger said, the nucleophile is part of the rate determining step in SN2. So the order of SN2 reaction with respect to the nucleophile is first order with respect to the nucleophile. So if we say double the concentration, we can expect to double the rate. How will increasing the concentration of the nucleophile affect SN1? It won't. It won't affect it at all because it's not part of the rate determining step. Yeah, we need some nucleophile. We need some nucleophile in order to do SN1. It shows up in the mechanism, but not part of the rate determining step. So we can alter the concentration of nucleophile all we want. We can't take it down to 0. We can alter it all we want, and it has no effect on SN1. But increasing the concentration of nucleophile increases SN2 because it is part of the rate determining step in SN2. So we can say that increasing the concentration of the nucleophile favors SN2. I assume putting nucleophile in brackets in Gen Chem, that signifies concentration of. Would you agree with that? Okay, how about the strength of the nucleophile? Using a strong nucleophile versus a weak nucleophile, where is that going to push this? Towards SN1 or SN2? Using a strong nucleophile pushes it towards SN2. Why? Don't tell me you don't know what to say, Jagger. I know exactly. I know you know what
I
to say.
do, but it's not going to sound very scientific. It'll convince the molecule to ditch the other one. It can.
Okay, fair enough. I'm checking with where your head's at. But all you really have to say is exactly what you said before.
Oh.
Part of the rate determining step. Part of the rate determining step. If we throw in a strong nucleophile, what impact is that going to have on SN1? No impact whatsoever. Because the nucleophile is not a part of the rate determining step. It doesn't matter if we have a strong nucleophile or weak nucleophile. What governs the rate of SN1 is forming the carbocation. Nucleophile is not involved in that. but the nucleophile is involved in the rate determining step for SN2, the one and only step, the rate determining step. So, a strong nucleophile favors SN2, a weak nucleophile favors SN1. Now please appreciate when I say a weak nucleophile favors SN1, a weak nucleophile isn't enhancing SN1. If it's not enhancing SN1, how can it favor it? They're cutting down on the competition. Again, two ways to win a race. You go faster, make the competition go slower. The competition to SN1 is SN2. We can enhance SN1 by making SN1 go faster. Well, this doesn't help. Or we can enhance SN1 by making the competition go slower, which is exactly what this is going to do. It's going to slow down SN2, therefore by comparison, SN1 becomes more prominent. The obvious question now is, no one has a question they want to ask about this?
What question do you want me to ask?
I want you to ask the obvious ones, yeah.
Okay, what is the obvious question?
What speeds up SN1?
Tertiary alkyl halide. There's nothing you can do with the nucleophile to speed up SN1. Okay, that's a good question. That's not the obvious one I had in my head at the time, but that's a good question. I guess in my mind, when looking at it, I guess in my mind, the obvious question is, how do you determine a strong versus a weak nucleophile? This is actually not that easy to do. Solomon's gives some things to help you, so you can make some predictions. But the bottom line is really, go into the lab and determine. For right now, strong nucleophiles, ionic nucleophiles tend to be stronger than non-ionic ones. So, for example, hydroxide is a strong nucleophile. Cyanide is famous for being a particularly strong nucleophile. And as we'll see over the course of the next 25 weeks, a particularly useful nucleophile. As far as weak nucleophiles, the most famous, well-known, if you will, weak nucleophile is water. It's a nucleophile because the oxygen has a partial negative charge and a couple of non-bonding pairs of electrons on it. So we can certainly envision it seeking out positive charge. But it doesn't have a full charge on anybody. It's a neutral molecule, so it tends to be a relatively weak nucleophile. Kind of the best known other weak nucleophile would be alcohols, which of course are just substituted waters. So for the same reason, they tend to be weak nucleophiles. I'll leave it at that for now. Okay. One other factor to consider at this point. Go back to Krista's comment, I erased half of it. Well, what about secondary guys? I haven't really said anything about secondary guys. Well, kind of the important thing to say here, the tertiary guys tend to undergo SN1. They're going to undergo SN1 pretty much no matter what you do with a nucleophile. They just don't do SN2. There's just too much steric hindrance. I don't care how strong the nucleophile is. I don't care how much you try and push it to SN2. It just really isn't going to happen. The primary guys really don't do SN1. I don't care how weak the nucleophile is. I don't care how much you try and push it towards SN1. They just don't do it. The primary carbocations are just too unstable. So pretty much everything we really said about the nucleophile applies here, really. This is where it's meaningful. Because these guys are the most influenceable. These guys are so biased towards SN2, it's very difficult to get them to not do that. These guys are so biased towards SN1, it's very difficult to get them to not do that. Here's Mama Bear, influenceable. So here we can definitely push things strong to the SN2 side by throwing in a strong nucleophile. We can push things towards the SN1 side by throwing in a weak nucleophile. Again, not that a weak nucleophile enhances SN1, but it slows down the competition, which is SN2. Okay. A third factor the nature of the solvent. There is a tendency in a class such as this to kind of ignore the presence of a solvent. I mean, we talk about this reacting with this to produce this. And we're all happy if we can figure out, oh, that's what's going to happen. But always implicit, unless we're talking about a gas phase reaction, which we about never are, implicit in all of our reactions is the assumption that we're dissolving this stuff in something in order to carry out the reaction. We kind of have a solvent. And that solvent can be very influential sometimes. We have a tendency to ignore it. Probably shouldn't. But in the first year class we do, and so I will. But not all the time. But you should always have in mind just that a solvent is implied. And the solvent can have a significant effect. Sometimes it doesn't. It can have a significant effect. Okay. So, in terms of a solvent, let's say we need to choose a solvent in which to carry out a reaction. The single most important factor, I'm going to call it an obvious factor, that we have to take into account when choosing a solvent is that the solvent must be able to dissolve the participants. By definition, the reactants have to dissolve in the solvent. So, given the fact that we're talking about nucleophilic substitution, alkyl halides reacting with nucleophiles, what can you say about the sort of solvent we're going to need? Do you think, for example, hexane would be a good choice? Or any other hydrocarbon solvent? Would that be a good choice, do you think? Bad choice. Because we're not going to get any of these nucleophiles to dissolve in something like hexane, a highly nonpolar thing like hexane. They're certainly not going to dissolve any ions or anything as highly polar as water and alcohol. Forget about it. You got to dissolve the players. So for nucleophilic substitution, we need something with at least some polarity. Because the things we need to dissolve have at least some to very significant polarity. So that's always number one. There may be some sort of theoretical reason why, looking at this thing, it would really help if we had a nonpolar solvent that would really push it, but if the nonpolar solvent won't dissolve the players, forget about it. It's just irrelevant. So we gotta have a relatively polar solvent. But within the broad category of relatively polar solvents, there can be more polar versus less polar within the still fundamentally polar region of solvents. In this context, talking about the solvent, we typically talk about choosing between what we call a protic versus aprotic solvents. Any guesses what we mean by protic? What that implies a proton. It's capable of maybe donating a proton. The way I just said it there, that implies like an acid, but not necessarily. A protic solvent is basically one capable of hydrogen bonding. When you have a hydrogen covalently bonded to a higher electronegative thing, that's going to give that hydrogen a significant partial positive charge. Maybe it's not going to be donated, fully donated as a proton, as like a bronzed-Lowry acid would be doing, but it's still a significantly positively charged hydrogen that can interact with something else, i.e. hydrogen bonding. So protic solvents fundamentally are capable of hydrogen bonding. Give me an example of a protic solvent. Water, there you go. Somebody else, another, not some human else, some solvent else. If not water, you might choose an alcohol, you might choose a substituted water. Those are probably the two most common protic solvents. And aprotic solvent, not capable of hydrogen bonding. So they can still be polar. So when we say aprotic solvent, we're not saying a non-polar solvent. We're simply saying a solvent not capable of hydrogen bonding. So, examples of protic solvents, water and alcohols are probably the two most famous examples. Aprotic solvents, DMSO is one of the most famous. That stands for dimethyl sulfoxide. And it looks like this. We've got a highly electronegative oxygen atom in there, so we can definitely see some polarity, but it's not capable of hydrogen bonding. Another example of an aprotic solvent, DMF, stands for dimethylformamide, which looks like this. We've got some highly electronegative atoms in there, so we can see this guy as being reasonably polar, but not capable of hydrogen bonding. Okay. Mickey's big hand says we're done, so tomorrow we'll talk about how these things can affect whether we go SN1 or SN2.